Hello everyone, I'm Billy Younger again, and this time I'm going to work out a problem of designing a banked curve where I do assume there's some friction to help the car make it around the curve. Again, I'm going to do it completely symbolically so we have an expression that works for all results. Algebra is a little bit trickier, but it works out pretty easily in the end, so I hope you enjoy. Turn on my document cam. Now you'll notice I've already drawn the vehicle and even started on the free body diagram so that I can save you some time. So what I'm saying is let's assume the angle has an angle theta, and that's what we're looking for. We'll see the vehicle has a mass m, it's traveling with a velocity v, and the radius of curvature is big R. So we'll use those variables as if we know them. We also are going to assume that it has a friction mu between the tires and the asphalt. So for whatever condition, you can look up the coefficient of friction, which may be static in the event that the vehicle is not skidding, or it may be kinetic friction in the case where it is skidding. So let's start off by drawing my free body diagram. There's the car right there with a mass M. The forces acting on it are, of course, the weight, which acts in a downward direction, which is a negative y direction. So I'm going to use orange for that. I just try to use consistently orange or red for the negative directions and green for the positive directions. So that's the weight. We also know that perpendicular to this uh, pavement is the normal force acting on the vehicle. So I'm going to draw that force. And notice I'm not using a particular color, orange or green, because this one hasn't been broken down into its components parallel to the x or y axes yet. So that's just the normal force. Similarly, I'm going to say that there's a friction force acting to help push the vehicle around the curve a little bit, and that's the friction force, which is mu times F normal. So that's the actual friction force. Again, this allows me the freedom of using the static coefficient of friction for any two materials in contact, as well as the kinetic coefficient of friction for any two materials in contact. Now my job is to just break these vectors into components, work out F equals ma, and see what we can come up with. So in this case, we're going to have a normal force that has a positive y component, and we're going to have a normal force that also has a positive x component. And we're going to assume the vehicle is coming at us and turning this way so that it needs its centripetal acceleration to go that way. That's what we're doing here. We also have a friction force that has a negative y component, but has a positive x component. So it'll be pointing this way. Now we just need to work out some of the geometry so we can figure out how to find these things. So this angle right here is the angle theta. So this is 90 minus theta, but this is also 90, so this must be theta as well. Since this is theta and this is 90 minus theta, this one must be 90 minus theta right here. Since this is, this is theta and this is 90, then this one right here must be 90 minus theta, which means theta should be up here. Or you can see that this and this are parallel. These are alternate interior angles, so that theta could also be put there. Either one's perfectly fine. When we do that, we're going to get Fn cosine theta for this component, Fn sine theta for this component. And over here, we see that this angle right here is in fact theta. That little angle right there is theta. So we can automatically see that this little force will be F times cosine theta, and that this little force is going to be F times the sine theta. And notice that one's negative. Excuse me, that's a script F for friction, sorry. Times the sine of theta. So we now have all our forces. All we have to do is use Newton's second law to work out the details. So the summation of the forces in the x direction equals mass times acceleration in the x direction. That is actually acceleration that way, which is level. And of course, the curve is going to be in a level direction. So we're going to assume the acceleration is centripetal and has to be this way. So that's the v squared over r. The forces acting in that way are F cosine theta, which is positive, and also Fn sine theta, which is positive. And that's it. That's the only thing pointing to the right and left, and that's going to be equal to mv squared over r. This is a v squared here. Sorry, I wrote on top of that F cosine theta, but I think you can see it pretty well. Now the summation of the forces in the y direction is equal to mass times acceleration in the y direction. In this case, we again are assuming the vehicle is not bouncing up and down, so the acceleration in the y direction really should be 0. So I'll cancel that out, call it 0. Now I just take all the other forces that are acting and set them all equal to 0. So it turns out the only forces that are acting are Fn cosine theta, which is positive, and then minus F sine theta, which is negative, and minus mg, and all that's equal to 0. I'm going to call this equation 1. I'm going to call this equation 2. And now we're just going to go about trying to solve for these so I can eliminate. Really what I'm probably going to try to eliminate is the normal force. But as you might guess, the normal force appears over and over again because remember, the normal force is actually part of the friction. So what I'm going to do first is actually take equation 2 and solve it for the normal force. So from equation 2, I'm going to say that the normal force times cosine theta is equal to mg plus F sine theta. But I got to remember that there's a Fn in there, so I'm going to say mg plus mu F normal, because that's what the friction force is, mu times F normal, times the sine of theta. So now I can get all the Fn's on one side, and this is supposed to be Fn as well. I just wrote F. So I get all the Fn's on one side. I'll say Fn, and this side is cosine theta. When I pull this one over here, it's going to be minus mu sine theta, and that's equal to mg, like that. So now all I have to do is say that Fn is going to equal mg over cosine theta minus mu sine theta. And I'll call this 2 prime. So now I can plug 2 prime into 1. And to do that, when I do that, I'll actually get some nice cancellations after a little bit of work. So plugging it into 1 is F cosine theta. So I already know that's mu times F normal. Well, F normal we decided was mg over cosine theta minus mu sine theta. And of course, that's mu times F normal times cosine theta. So I got a cosine theta over here as well, plus Fn times the sine of theta. Well, again, that's plus Fn is equal to mg cosine theta minus mu sine theta, like so. And then, of course, I still have the sine theta left there. And then on this side, I have equal to mv squared over r. So I can see now that there's a common m term in both of these as well as that. So in principle, I can go ahead and cancel out the masses. That's good to hear. Turns out that even the frictionless situation, or even a friction-full situation, the ultimate angle is probably not going to depend on the mass at all because we just canceled the masses out. I do have a common factor of cosine theta minus mu sine theta, so that could come in handy. And I've got a common factor of g, so that could come in handy as well. So let's work a little bit and see what we can do to make this work a little better. If I do that, then all I have to do is combine similar terms, if you will. So what I'm going to first do is I am going to, since I have a common denominator, go ahead and make use of that common denominator. I'm going to say mu g cosine theta plus G sine theta. That's me adding the two numerators. All of that over cosine theta minus mu sine theta. And all of that's going to be equal to V squared over R. So what I'm really trying to get to is the individual thetas. So I should try to get all the thetas related to one another in some way. You might notice that if I multiply by cosine over cosine, this whole side, excuse me, 1 over cosine over 1 over cosine, notice that I am multiplying by 1 because I'm doing it to both the top and the bottom, so I don't have to do it to this side. But when I do that, I get a pretty nice cancellation because the cosine over the cosine just becomes 1. So this side, the top is going to become mu g plus g, and then sine theta over cosine theta, which we're going to know is tangent theta, but I'll write it like this first. And then the same thing is going to happen over under here. I get 1 minus mu sine theta over cosine theta is equal to V squared over R. So that's kind of nice as well. And we can see that I'm both going to have two tangents in here. So what I'll do is multiply this R through all this junk and multiply this times the V squared, and I'll go ahead and convert those to tangent thetas. And what I'll get is mu times R times G plus R times G times the tangent. Oh, sorry about that. Times the tangent of theta is equal to, now I'm going to do the V squared on all this junk. So the V squared is going to hit the 1, and I'll get V squared minus mu V squared tangent theta. So now I got a common term of tangent theta on both sides. So I can get, I will pull this one over to here and pull this over here. So I'll get R times G times tangent theta plus mu V squared tangent theta is equal to V squared, that comes from that one, minus mu RG. I can now factor out a tangent theta, and I will get tangent theta times RG plus mu up times a V squared. I forgot the V squared equals V squared minus mu RG. So now all I have to do is say theta is equal to the tangent inverse of this thing, which would be V squared minus mu RG over this thing, which is mu V squared plus RG. And I think you can see what happens with that. That is sort of like what we expected, because in the event that mu was 0, this term and this term over here are going to disappear, and I'll just get V squared over RG, which is exactly what we got when we were solving for the frictionless problem. So that gives me some confidence that the answer is actually correct, and that is the final answer. I hope that helps you understand how to solve physics problems. Have a good day.